Okay, let's get started. Thank you everybody for coming. I'm delighted today to introduce our colloquium speaker, Professor Karen Masters, who has come to us from Haverford College in Pennsylvania. Professor Masters was previously of the Institute for Gravitation and Cosmology in Portsmouth, and before that, Harvard and Cornell and Oxford. She is an expert on extragalactic astronomy, in particular working with a bunch of large surveys and large collaborations. So is I'm going to get the wrong way around, the PI for Galaxy Zoo, yes, and the spokesperson for SDSS4. Obviously, I'm never going to be the spokesperson, given that. Yeah, for SDSS4. So she's working a lot with these manga galaxies, Slow Digital Size Survey, citizen science, and we're going to hear about some of that today. And she's going to tell us about spirals in galaxies. So please take it away.
Thank you, Chris, for a very nice invitation or introduction, and for the invitation to come and speak today. So I'm going to talk about spirals in galaxies. As Chris mentioned, I have broad interests in galaxy evolution with a kind of focus on why morphology is interesting and what morphology can tell us from big surveys. But in particular, this talk came out of some work I did on my last sabbatical, which was a COVID sabbatical. So I spent it in my basement, spending a lot of time, well, it's okay, it was fine, talking with Jerry Selwood about spiral structure, and we worked on this review article. So I'm really going to focus on observations of spirals. I'm well aware that there are some people in the audience who spend a lot of time thinking about the theory of spirals, but of course, maybe not everyone does that. So I do have some introduction to why spirals are interesting and some of the background about what we know about spirals. And then I'll kind of focus on observations I've been involved with the projects I work on. So it is a little bit biased towards the work myself and my students have done, but hopefully you'll forgive me for that. So spirals have been observed in galaxies for almost around 200 years, I would say. I just always enjoy starting with this drawing of the Whirlpool Galaxy done by an astronomer from Ireland in the mid part of the 1800s, comparing it. It's the Whirlpool Galaxy, right? So this is the Hubble image of the same galaxy. So this is the first recorded observation we have of spiral structure in galaxies. And people were obviously very struck by this. So there are suggestions that it was the inspiration for the spiral in the middle of Starry Night. So these are beautiful objects and fascinating objects with some really interesting dynamical physics. If you've taken an astronomy class or taught sort of Astro 101, you've probably taught about the classification of galaxies using the Hubble tuning fork. So it's just a good reminder of the kind of big picture here of galaxies. Edwin Hubble looked at photographic plate images of around 1,000 galaxies and put together this classification scheme in the 1920s, where we have elliptical galaxies, so these smooth, reddish, the more massive galaxies on one side, and spirals on the other side, with this fork set by whether or not they have a galactic bar, this linear structure across the middle. The diagram here is Hubble's sketch, and the images are his example images, but SDSS versions of them. So one other note on terminology, I already mentioned ellipticals tend to be red, spirals tend to be blue. You can see that actually in the SDSS images that I've put here. We also tend to use early type for things at this side of the diagram and late type for that side. One of my pet peeves is people then go on to say, and Hubble thought this was an evolutionary sequence. It's not true. You can find a footnote in one of his papers about how that was not true. And he was just using an analogy to late and early type stars to provide some names. He never thought it was a sequence in time. Random aside to my pet peeve. So you've probably either taught this or seen it in a class. Since we're talking about spirals, a little bit more detail about the spiral part of the sequence. So spirals are ordered from an SA, an early type spiral, to an SC, or a late type spiral, based on two or three different properties in Hubble's classification. And so sort of implicitly, we're saying these properties correlate with each other, right? So SAs in Hubble's language have large bulges, tightly wound spirals, which are very clear and distinct. Whereas you move to SCs, where you have small bulges, loosely wound arms, and the spirals tend to be patchier. Another interesting side note, so as as recently as 10 years ago, Ron Buter, one of the real experts in traditional morphology, is talking about how if there's a conflict here, so if you have something with a large bulge and loose arms, or a small bulge and tight arms, you should classify it based on the arm winding. That is just not what's done these days in big surveys. This distinction between early type and late type spiral is almost entirely on bulge size in big surveys. So just to note that those two things are different. Okay, there's more complicated classification schemes for spirals. So de Berkeley in the 1950s had this sort of wheel thing where we would put spirals and rings on a classification scheme. This doesn't work very well, sorry. One of my favorite words in astronomy, flocculent, is meaning literally fleece or cloud-like, these sort of very patchy spirals, as opposed to grand design, the very large scale, stretching across large radial range, typically symmetric. This was a classification or a separation developed by the Elmegreens in the 1980s. And you see spirals all over the place. So there's something very interesting and like generic about spirals in dynamical systems made of large numbers of particles. So just some examples of spiral in a protoplanetary disk in the Ophiuchus star formation region. You can make spiral in the cream in your coffee cup. Saturn's rings actually are extremely tightly wound spirals in places. And of course, hurricanes, spirals. A little bit of a spiral math now. So in nature, most of these spirals are something called a log spiral. So you have the log of the radius is proportional to the azimuthal angle, and the angle that this log spiral makes to the tangent to the circle at the same radius is called the pitch angle. And in a log spiral, that pitch angle is constant with radius, so it's one number. So, you know, Nautilus shells, Mandelbrot sets, all kinds of things are versions of log spirals mathematically. So again, just a reminder, large pitch angle is very open spirals. So 90 degrees would be spokes, like in a bicycle wheel. And a pitch angle of 0 is a ring. So if you've taken a galactic dynamics class, you'll have heard of the winding problem. But just a reminder, of what this is, right? Galaxies rotate differentially, and very famously, right? They have flat rotation curves with radius. So that's the flat circular velocity. That means the inner part does more rotations in the same amount of time than the outer part. So if spirals are material structures, if they're like ribbons, they would wind up over time in a galaxy. So of course, this was the original argument that they cannot be material, they must be some kind of density wave. A reminder of what a density wave is, using an analogy with cars instead of stars. It's a really fun little video that a student of mine found once, where it's a circular, well, the cars are driving in a circle, and you're going to see a little density wave get set up over here. So you can see, right, the density wave starts to move this way, actually, but the cars are moving this way through it. So the idea is in a spiral galaxy, the spiral arms are this kind of feature, right? The stars are bunching up. Obviously, they're not changing speed in the traffic jam like cars are. The density is very low, right? They're not interacting with each other. But the spirals are places in the galaxy where the orbits of the stars are bringing them slightly closer together. So density waves. So this is another classic diagram talking about these sort of elliptical orbits of stars in a galaxy, and you can start to orient them appropriately that they end up looking like spirals. Many people, I think, would agree that a large number of spirals are driven by tides, interactions with galaxies. So the Whirlpool galaxy is the prototype of this, with its companion clearly connected to the spiral in some way. There's also discussion of how the galactic bar might drive spirals in some cases. It's definitely the case observationally that barred spirals are much more likely to have two arms, two spiral arms, than other numbers of arms. So there appears, at least superficially, to be a connection between bars and spirals. Oh, I find this one interesting, and maybe everyone knows this, but I didn't know this until I was working on the review. Density waves should trail, which means the spiral arm, the sense of the arm is that the galaxy is rotating this way, right? So the arm is sort of trailing behind the rotation. You can't have a density wave that goes the other way, I think. Someone can correct me on that if I'm wrong. But it's actually a really hard measurement to make. We're good at rotation in galaxies observationally. The Doppler shift works really well. We can get the rotation really easily. The tricky thing is determining the orientation of the galaxy, what the front is and what the back is. This diagram makes it look not tricky at all, because these are beautiful examples of galaxies where you can tell because of the dust lanes. And so these are de Vaucouleurs sketches of these galaxies, where you can see like this is the front because the dust lane cuts across the bulge. And you can see a little dust lane here. So this is the front. But it's not as, if you look at just a general image of a galaxy, it's not that easy to tell. And it's certainly not something you can automate very well. So we've actually only done this in around about 100 galaxies to determine observationally that they are actually trailing. And almost all of the 100 are trailing. So there's no cause for concern. But I just think it's interesting that in today's sort of big data astronomy, we only have this measurement for 100 galaxies. Yeah.
There are ones that are not, or
There's
just...
a couple, yeah. And people sort of argue about them in the literature a little bit, why that might be. But yeah, there is at least evidence. There's a couple of spirals where there appears to be some trailing and some leading arms, which is very weird. There's a lot of galaxies, so there's always some weird ones, yeah. Okay, but back to density waves. You know, we said there might be some kind of effect of environment driving spirals. Certainly there's, you know, we know that galaxies interact a lot with their environment. Bars may have some kind of role to play in driving spirals in some galaxies, but there are very isolated spirals that don't have bars. And they still have spirals. So there must be a way to generate spirals fairly independent of, you know, other stuff going on. And one of the sort of interesting things that's happened in the last, I guess, 10 or more years is that in numerical simulations, so this is a hydro simulation, has stars and gas, we're seeing the spirals actually are winding to some extent. They are still density waves, so they're not winding as fast as they would if they were material, but they are not, they don't have a constant pattern speed with radius, so they're not rotating at a constant pattern speed. They are winding up over time. So one way to generate that Jerry Selwood has worked a lot on are these self-excited instabilities, so overlapping modes in a galaxy. I'm not particularly a dynamicist, so I like to kind of think of physical analogies for what is going on here. So I sometimes think about like wave interference patterns. You get a very coherent pattern from multiple waves overlapping. Perhaps a better analogy is this kind of beautiful patterns you can get from applying sound waves to metal plates. So you can get all kinds of interesting patterns. You know, in a spiral galaxy, of course, right? It does have an edge, but the edge kind of fades off. It is rotating, so there's some, you know, frequencies which are special. But the idea is you can end up with density waves that wind up that are caused by these sort of overlapping modes making patterns that change over time. But others can probably explain it better than me. And there's other ideas for how isolated spirals can form in galaxies, and there's a lot of galaxies in the universe. So probably if it's physically plausible, it's happening in a galaxy somewhere. So my summary sort of the introduction here, what we know about spiral arms and what some of the questions are that I'm interested in. You know, we know they're density waves, but they're probably not static density waves exactly. They may be winding up over time. There's some evidence in the simulations for winding, and I'll show you some observational evidence which might hint towards winding going on. There's probably a link to tides and maybe bars, at least for some spirals, but there are spirals in isolated galaxies that don't have bars. And I think, you know, in observational extragalactic astronomy, the big question really is, does it matter? Do they actually have an impact on galaxies? Should we care about it in terms of the evolution of the galaxy? Or are they just kind of a detail that's nice to look at? So I've worked with the Sloan Digital Sky Survey for a really long time, not 23 years to be fair, but a long time. And so I probably don't need to tell people near Princeton too much about the Sloan Digital Sky Survey, but just to place in context that I'm working with these kind of big surveys where we have data for hundreds of thousands, or in some cases even millions of galaxies. But spirals are really complicated things. They're not a simple thing to measure from a lot of images of galaxies. So I don't know if you've ever seen Marshall's versus the Machine, but it's a cute kids movie where they defeat the machines by confusing them because machine image recognition algorithms can get confused by similar looking images that are actually very different and obviously different to people. So the puppy versus bagel is another version of that. You can find other examples on the internet. So I've been involved for a long time in leveraging the fact that people are really good at image recognition. If we can collect lots of people's opinions of what things look like in some kind of statistical way, we can use that for science. And we'll come back to machines getting involved later as well. So this is Galaxy Zoo, which is a crowdsourcing project that's been running now for 16 years. It's a very well-established project. We put images of galaxies into a website, and we invite people to classify what they see in their images of galaxies. We try to keep the questions quite simple, so it's not interpreting what you see, it's just saying what you see. And we ask a lot of people per galaxy so that we can get good statistics on the answers. And we've done this for a lot of surveys now, so the SDSS surveys, all public HST surveys. UKIDS is a British infrared survey, which we have yet to publish that one, but we have done the classifications. A lot of the images that have been on the site recently are from DECLs, the Dark Energy Camera Legacy surveys, and Mike Walmsley has led a lot of that work. And this is where the machines are starting to get involved and be in the loop to help us accelerate what we can do with Galaxy Zoo. And we've also classified some simulated galaxies in Galaxy Zoo to see how the population that the simulations make compared to the population that we see in the real universe. Oh yeah, and right now we have some JWST Sears images on the site, and we're hoping to do more of the public, or the to-be public JWST imaging surveys in the future. So the idea behind Galaxy Zoo was pretty simple, and this is before I became involved. I started working with Galaxy Zoo about a year after it launched. It's really easy to tell a person the difference between a spiral galaxy and an elliptical galaxy. You just tell them that, and then you ask them to go classify them, and you collect statistics on what they answer. This worked really, really well and was really, really popular. So it's a BBC News article from 2007 about seeking help looking at galaxies. Became the, which one is it, second most emailed story on the BBC website for a time. The classifications per hour really took off. So after a few hours, we think when the East Coast of the US started to wake up and read the news, it really started to take off. We were up to 40,000 classifications per hour in the first day of Galaxy Zoo, which it crashed the SDSS servers, which again, I wasn't involved at this point. So these days, the images are hosted on a cloud server, which can react if there's some event that drives a lot of people to the site. So just highlighting, this is from the article, the hope is about 30,000 people might participate. And we like to thank our volunteers in papers. So the first paper out of Galaxy Zoo had 160,000 volunteers. This is 200,000 volunteers, another 85,000 volunteers. We do count who did which phase, so we can have good statistics. So this is not, there's some overlap, but so a lot of people are doing this, and it continues to be of interest today. We don't collect 40,000 classifications per hour anymore, but we still get about 15,000 a day. So we can still classify pretty quickly sets of images. And we like to collect 40 classifications per image, something on that order, so we have good statistics. And one of the reasons for wanting that large number is that we now ask somewhat more complicated questions. We don't just ask, is this a spiral galaxy or an elliptical? People turn out to be really good at that division, and so we ask more complicated things. And this is where you start to get back to spirals. So this is an example classification for this galaxy. If you care, it has its classical morphology down here, all the different things. So the first question is there, do you see a disk or a feature in this galaxy? And you have to say yes or no. You'll notice that we say that 39.019 people classified this galaxy, so that's obviously not possible. And that reminds me to tell you about the post-processing we do. So if someone comes in and says, haha, I'm gonna mess with Galaxy Zoo and I'm gonna do it all wrong, and I'm gonna say that school teachers do use this in the classroom, so it probably does happen, right? So we actually do go through with an algorithm and check if someone consistently disagrees with everyone else, we downweight their contributions so that they don't contribute. So that's why we have non-integer numbers of people. And so then, of these 39-ish people, 38 said they saw this sort of feature. So there's always one, right? But that's okay. If we have 38 out of 39 saying you see this sort of feature, you're pretty sure that you've got a this sort of feature. And if this split is closer to 50-50, you know that's hard to classify. So it's not zero information if it's 50-50, right? So we're starting to move to having a probability-like number that goes from 0 to 1 that tells you whether or not the feature is present in the galaxy. Probability-like numbers are great for doing data science type things at the other end of the process, right? Anyway, so we've got our 38 people saying they saw a feature or disk. They're then asked if it's face-on. So again, 37 of them agreed that this galaxy was a face-on disk. And then they're asked about bars, spiral arms, the windiness of the arms, how many arms there are, about the size of the bulge, and other things. We actually have other more complicated questions that you can answer later. So as you can see, when you start with 40 people, we come down to having 11 people saying that this has 2 arms confidently. So there's a little bit of like dealing with the fact that it's a tree and you have to think about how many people out of how many people answered a specific question. Okay, so we've done a lot of science with this. We're a pretty small science team, actually. It's a lot of volunteers and a really big footprint in the sort of popular science world. But in terms of the scientists working behind the site, we've always been pretty modest in scale, just a handful of people. So I'm pretty proud of the fact that over around about a decade, we have 77 official team publications. We're very open collaboration. So if you have something you're interested in doing with galaxy morphology, please reach out and we'd love to talk with you. We have a number of papers with a lot of citations, which I'm really proud about. A lot of these are the data release papers, which makes sense. A lot of people are using the Galaxies catalog to do their own science, which is fantastic. But we also have papers about the extragalactic work. In particular, a number of papers about the correlation between color and morphology. We talked at the beginning about red ellipticals and blue spirals, but how well does that work in large populations? Finding interesting and odd things. So computers are great at answering what you ask them to tell you. Humans are curious and will sometimes tell you things you never asked them or never thought to ask them. Yeah.
To do color and morphology? Do you have them do some calibration step for the color of their monitor, or?
We get the color in the standard astrophysical way. So the color is from apertures and photometry. We don't ask people about color. We're only asking people about morphology. Yeah. Yeah, and then we can find samples by morphology, or we can look at the morphology of specific samples of galaxies. And so some examples of that. Okay, so back to spirals. So a reminder, I already showed this slide, right, about the classic spiral sequence and this implicit statement that how tightly wound the spirals are should correlate with bulge size. So we asked those two questions separately in Galaxies, so it seemed interesting to check. We didn't exactly ask about pitch angle. We asked how tightly wound the spiral arms appear, but we've done a number of checks of how well this correlates with pitch angles measured in more traditional ways. It turns out to be really, really hard to measure pitch angles for a variety of reasons, but this does seem to work reasonably well, probably as well as other methods. So this was our result, which we published in 2019. So we plot on the y-axis our measure of pitch angle at some level. It's a combination of different answers from Galaxy Zoo, such that loosely wound spirals are down here and tightly wound are up here. And it managed to get a single number from 0 to 1. And then this is also a bulge size score coming out of Galaxy Zoo. So small bulges are close to 0 and large bulges are close to 1. It's not exactly bulge to total in the traditional way. There's just a random diagonal line plotted to guide the eye, I guess. And then the red and the blue lines are the averages, binned averages in the two directions. So we were surprised to see basically no correlation. And this is a volume limited sample of almost 5,000 spirals. That seemed very contrary to what we had learned about the spiral arm sequence. So that's really interesting, right? And you want to dig into it a bit more. One thing we did was separate it into whether or not galaxies had bars. So I think this is just interesting side. While there is no correlation evident in either, which way around is it? The unbarred side or the very strongly barred galaxies, and there's a population in the middle that have ambiguous, maybe weak bars. There's no correlation in either, but there is a shift, right? So the unbarred galaxies tend to be more tightly wound at the same bulge size than the barred galaxies. We did this here. This is also some nice work by Russ Hart, who was a PhD student in Nottingham, did more traditional pitch angles as a function of the bar likelihood. So strong bars over here, no bars over here. You can see pitch angle growing with bar probability. So there does seem to be a connection between bars, the presence of bars, and the pitch angle of spirals, which is interesting. It's always more complicated with galaxies. Oh, and this plot doesn't show it very well. My apologies, but you'll have to go read Petra's paper. So Petra is an undergraduate at Haverford working with me. She's a senior this year, so she'll be applying to PhDs this year. And what we did was the same thing that I'd done in 2019, but splitting the spiral galaxy population into red and blue spirals, just using color, optical color, and massive and low mass spirals. And so basically, if you have massive spirals, either red or blue, they have the opposite correlation to what you can read about in the Hubble sequence. If you go for low mass red spirals, they have no correlation at all. If you go to low mass blue spirals, the kind that are really visible in the local universe in photographic plates, for example, of the kind that Hubble probably looked at, you do see a correlation. So that kind of makes sense. You do see the expected correlation. It's not very strong, but it is there. What was interesting in this also is that blue spirals tend to have more loose arms, which we'll come back to. And there's also a mass dependence. Massive spirals tend to have tighter arms in the population. I promised a mention of this project. So this was a PhD student I worked with in Portsmouth who graduated in 2020. This was a side project in Galaxy Zoo. Tim now works as a data analyst. Actually, he's worked for a number of companies. He's a very, very talented data scientist. So he ran this project where we actually did in-browser fitting of models. So the citizen scientists tweaked a multi-component model of a galaxy to fit the light. And the thing that we could do that's really hard to do in an automated fashion is try to fit the spirals. So Tim had a number of, I forget how big his sample is, but he had a number of measurements or indicators of the spiral pitch angle. One thing that we quantified, and other people have done this as well, but I think it was nice to see it done in this sample, is how the pitch angle can vary quite a lot between arms in a single galaxy. So it's not necessarily a single number for a galaxy. So this was that plot. Hello?
More what we're actually looking at.
Sure.
This is one object that we're looking at, or
no, this is multiple objects. And then the black lines are multiple people's indication of where the spiral is. And then the red is some optimal clustering of those lines that is constrained to be a log spiral, actually. There was not enough statistics to suggest that it should be anything other than a log spiral, so we went with log spirals as the simplest mathematical model. Yeah?
do you attempt to rectify these images before you present them?
That's right, yeah. So by rectify, you have to deproject them, so make them be face on, which is definitely something which can introduce error. Right, and so the inter-arm variability that we found. So by that, I mean the difference in pitch angle between the three red lines here averaged at 11 degrees. And so that's that. This is the difference between the average for the galaxy and then each individual arm as a function of the average for the galaxy. So the scatter here is about 11 degrees. Tim also looked at trends with bulge size and agreed with our more simple analysis. There was no trend in this sample of pitch angle with bulge size. And this is bulge strength from the model that we fit, so from photometric decomposition. He also found no trend with bar, the presence of a bar. So that was disagreeing with our earlier work. So that's interesting. but some interesting statistics. And one thing he also did was look at a comparison with the expected distribution of pitch angles, so cotangent of pitch angle, from this model it's not really a model, but it's a suggestion from Pringle and Dobbs 2019, that if you have a population of spirals that are winding, you should end up with a distribution of pitch angles that is uniform in the cotangent of the pitch angle. And you'll have to quiz me later on the details of why that works, because I'll have to remind myself. But what we found was the distribution of pitch angles in this sample of galaxies matched that prediction pretty well. So it was consistent with being uniform in the cotangents of pitch angle. So plausibly evidence for winding. Okay, shifting gear a little bit to talk about star formation. So spirals are density waves in a galaxy. So there's two ways that should impact star formation, or that could impact star formation. You may well have heard of the Schmidt-Kennicott relation, right? Where you have more dense gas, you have more star formation. That's a really clear correlation between the density of gas and star formation. So if you have an overdensity in gas, you should have more star formation in that overdensity. The other thing that can happen, and that was, I think, first talked about in 1969, the density wave itself, as it passes through a gas cloud, can create shocks and cause star formation to happen. So it's this beautiful illustration of this happening in this NGC 5247 grand design spiral, where the different like X's and dots and things are tracing out the spiral in different bands of light. And this is not work I've been involved in. This is Lewis Ho's group, work from Lewis's Ho's group. And so you can see that as you go from far UV through near UV, blue, as you get redder, inside co-rotation, which is the circle, the gradient goes in one direction, and outside it goes in the other direction. So this is a signature of this density wave passing through and generating star formation. And then as the stars age, they're progressively behind where the spiral passes through the stars, or if the stars are passing through the spiral, the trend flips. And that flip will happen at co-rotation.
Coincide with that flip.
I do not remember. We were talking about that earlier, and I should have looked that up, but I don't remember. Probably is my guess. Yeah. All right. So what do we know about this from Galaxy Zoo and the work that I've been involved in? So this is one nice result, looking at how spiral arm number correlates with galaxy color. So each of these little diagrams is a color mass diagram. So it's a little bit like mass star formation rate, which is a more like theoretical way of putting it, but we actually observe color or something that correlates with star formation. So up is red, down is blue, which means up is less star forming, down is more star forming, and we have normal masses. So all galaxies are the like grayscale, which is the same in every one, and then we're over plotting a contour of where you get spirals that have certain numbers of arms. And you can probably see that they get bluer as you get more arms. So m equals 1, kind of weird. M equals 2, most spirals are m equals 2. Like this is by far the largest population, so this is most of the spirals. M equals 3 are much bluer, 4, 5, much bluer. So it's clearly a correlation with the color of the galaxy and the number of arms. Although when Ross dug into this a lot more in his beautiful PhD work, it actually turned out to not really be a difference in star formation rates. It was more about dust obscuration and how much of the star formation was obscured. A really neat piece of work. That's just from photometry. Chris mentioned I worked with SCSS and the MANGA survey, which is spectroscopy a lot. So we're just gonna have a little quick reminder of what we can learn about galaxies from spectroscopy, from optical spectroscopy. And then I'll tell you about some MANGA work that we're doing right now. So remember, the spectrum of a galaxy is the sum of the spectra of all of the stars in the galaxy. So if you're looking at a galaxy that doesn't have any active star formation going on, you're just looking at light from stars predominantly. So you have the continuum is just the sum of their continua, and then you end up with absorption features from the atmospheres of the stars. And so that's how you get your metallicities and your redshifts. There's no emission lines because there's no ionized gas in this galaxy, because there's no star formation in this galaxy to first order. The other thing to notice is this break at 4,000 angstroms. This is caused by a lot of different metal lines in cooler stars. And so it gets bigger and bigger. The sort of jump you get at 4,000 angstroms gets bigger and bigger as the stellar population ages, and you lose the hot, massive stars, and you start to see more of the light from the low mass stars that live for a really long time. Let's switch to a star-forming galaxy instead. So immediately you can see the continuum is bluer. Because it's actively star-forming, it still has O and B stars that are bright and dominate the light. You have a weak break at 4,000 angstroms. You can still see the absorption features, but you also see these very distinctive emission features that are coming from the ionized gas recombination lines from ionized gas around star formation regions. So really distinctly different, and we're learning a lot about what kind of stars are in the galaxy from the spectra. So MANGA is a spectral mapping survey. So if you've worked with spectra of galaxies, most people, the biggest sample is the SDSS sample, which put a single fiber on each galaxy. And for very nearby galaxies, that single fiber is very much in the center of the galaxy. MANGA instead, the biggest array, had 127 of those fibers in a hexagonal array. And so you get a spectra at every point across the galaxy. Okay. So this turns out to be pretty complicated data. We call these data cubes. So you get basically an image of the galaxy at each spectral resolution element, or you can do some analysis on the spectra and generate maps of properties that come out of the spectra. So here are some example maps of properties you can get out of a MANGA data cube. So maps of the H alpha emission, that emission line of hydrogen, maps of nitrogen emission line, an oxygen emission line, silicon emission line. The Doppler shift is really helpful in astronomy, right? So we also get information about how the gas and the stars rotate separately. And you can, and the random motion of stars, you can also fit models to get information about the stellar population. So you fit stellar population models and get stellar masses, metallicity,s and so on. Lots and lots of information for lots and lots of galaxies. So in total, MANGA did 10,000 galaxies. This is them on a color magnitude diagram and a star formation rate, stellar mass. It's not a complete sample of the local universe. It is a representative sample. So we oversampled rare galaxies, but it's embedded in the bigger SDSS sample. So there's weights you can use to recreate a volume limited sample. This is not 10,000 MANGA galaxies. It's some subset of them, but this is a cute little diagram that Carl Westphal made, making the name of the survey in the GRI images. And I'll flick through some other properties from MANGA in the same order. Maybe, oh, I went too off. There we go. This is the H alpha flux of the same one. So you can see where things have a lot of ionized hydrogen and where things don't. That D4000 measure, which I said correlated with stellar age pretty well. So you can see the old stars and the young stars, or galaxies with old stars, galaxies with young stars. Stellar velocity, lots of things. So MANGA's been really, really great. And one of the big things that's come out of MANGA is lots of papers looking at gradients of properties from the spectra. So to get a gradient in MANGA, you put these elliptical isophotes over your galaxy, and then you average the measurement in each of these elliptical rings, and then you just plot that as a function of radius. This is actually not, each of these lines isn't a single MANGA galaxy. Each of these lines is the average of a bunch of MANGA galaxies at the same mass. This is really nice work that shows how gas phase metallicity measured in the MANGA spectra, how the gradient of it is different for the massive galaxies, the red lines, and then you get very shallow gradients for low mass galaxies. You can also fit straight lines to this and then plot gradients of properties against something else. So that's what this work is. This is the gradient of DN4000. So the gradient, kind of like the rate of change of the age of the stars as a function of radius against what the central value is. Some very interesting work. So we thought it'd be interesting to add in some morphology here. And this is some work that my student Emmy Weiss has been doing. She graduated from Bryn Mawr last year. Bryn Mawr and Haverford are this bi-co agreement. So I supervise a lot of Bryn Mawr students for senior thesis work. Emmy is also applying for PhDs this year. She's working at the Mariah Mitchell Observatory this year. And so we thought it'd be neat to do those metallicity gradients as a function of spiral pitch angle and see if there's any impact. The idea kind of came out of some work by Kate Daniel, who just recently moved from Bryn Mawr to Arizona. She's a dynamicist and had some predictions that more loosely wound spirals should drive more radial migration. So the idea here is, your galaxy gets set up with a radial gradient because you've got more star formation in the center, so more metal rich in the center, less metal rich in the outskirts, and any kind of radial migration should shallow that gradient. That's the idea. So we thought we'd look for that. And so that's the result is here. It's a little bit complicated, but which way around is it? Color is the arm winding. So if you just look at the dotted lines, this is our lower mass sample. We split it by mass because there's clearly a mass dependence of these gradients. And in the lower mass sample, whether they were tightly wound arms, the green line, medium, or loosely wound, the pink, really separated out these metallicity gradients, which I don't really know how to interpret yet, but it's there in the data. So I thought it was interesting. In the more massive spiral samples, we didn't see any impact from spiral winding. But I think this is really interesting work, and Emmy's currently working on writing this up for publication. So we didn't just do spiral winding, we actually looked at other morphologies on the impact of them on these gradients. But this was the most interesting effect. So we could do this radial averaging and just come up with gradients, but there's actually a lot of really beautiful complexity in the manga data. So again, some maps from manga compared to their images, and you can see spiral structure popping out in the maps of properties. Even this D4000 has some hints of spiral structure in it from the age of the stars. I'm almost done, I promise. So we wanted to go beyond gradients, and to do that, we needed to be able to pick out the spectra from manga in specific regions of the galaxy. So that would be an interesting crowdsourcing project. And so we ran this Galaxies 3D site, 3D because of the data cubes from manga, where it asked people to look at images of galaxies and draw on them where they saw certain features. So this ran, and we have done the analysis to get the results. And we end up with these sort of heat maps, which show you where the bar is in orange, where the spirals are in blue. We also ask for the centers of galaxies and foreground stars, because the foreground stars mess up a bunch of the pipeline. And this is all available. We published it a few years ago, and you can use it with the manga data to do things like this. So this is the flux in H alpha as a function of azimuth around the galaxy in the spirals, the blue, so you can see the up and down of the spirals, and in the bar in the orange, and all kinds of other things with it. The spiral masks are a little bit tricky to work with. I think I'll skip over this a little bit in the interest of time. You have to pick a threshold level where you believe that it's a spiral. But one thing we did do, again, an undergraduate project looking at the amount of star formation there is in spirals compared to the star formation in the whole disk. So we were able to show from this measurement that there's an excess of star formation in the spirals, and actually an excess which grows with radius. So this would be no enhancement of star formation in the arms, and you can see as a function of radius, you get a larger and larger fraction of the star formation by area is in the spiral arms. And this is Masha Kilobata, who's a sophomore at Haverford. Really, really fantastic student, has been using these masks just this past summer to look at the mass excess in the spiral arms. So we use a model for the stellar mass surface density fit to the spectra, which is published in Sanchez et al. 2021, this pipe 3D model. Apply the spiral masks. So you can't really see it too well, but there's like a little faint blue line that is around the spiral arms in this galaxy. That was our arm measurement. We have a little white bit where we sort of just throw out the data because it's ambiguous, and then we have an inter-arm measurement that's not surrounded. And so what Masha showed is that in both of these regions, the stellar mass surface density drops exponentially with radius, but it drops more quickly in the inter-arm regions than the arm regions. So you have this excess stellar mass surface density, which grows with radius. It goes from about 15% in the inner parts to 30% in the outer parts. I think this is really cool.
Okay, so fitting to exponential.
Effective radius is from, yes, photometric model fitting.
So that is, you're saying that the effective radius in the arms and inter-arm regions are different?
Yeah.
That's very cool.
It's interesting, right? Yeah, and so you're right, this effective radius is the whole thing. But clearly they have different effective radius. Yeah. So we still have some like data cleaning to do before we'll publish this, make sure that the masks are really good and that we have the right sample of galaxies, and think a bit about the observational biases. Like these are the spirals we can see, which worries me a bit about this measurement, but I think it's a really neat measurement and I hope we'll publish it soon. Yeah, so that is the end of what I wanted to talk about with spiral arms. I've definitely not covered everything we know observationally about spirals, but just a flavor of things I've worked on. We just end with the questions that we started the observational section with. There is, again, some evidence for this winding. There's a puzzle about isolated galaxies, maybe, or maybe not, I don't know. And there definitely seems to be a link between the arms and star formation and stellar mass surface density excess that we can measure really nicely with the MANGA data. I'll skip over. I had a few backup slides, which I will skip and just end with thanks and some pictures of my research group. Thanks.
Would you care to comment on inclined ridges between spiral arms of stars and presumably gas and their mechanism of formation?
Inclined ridges?
Between adjacent spirals, there are little ridges of gas. Comment on that?
I don't know anything about that. I've definitely, I know what you mean, but I don't know.
Yes, yeah, absolutely.
What do they call them? Feathers, kind of, right?
Yes. I discussed that, but
FANGS data from JWST, you have these seemingly large arms that have these sub-arms coming off them. So there is a whole theory for that.
Ridges between adjacent spirals.
Yeah, I'm definitely working in a redshift regime where those are not really clear. The FANGS data is just beautiful for that kind of thing. Obviously a much smaller sample though, much more nearby.
What bars can do is transport angular momentum. So has anybody looked at correlating either AGN activity or nuclear star formation with bars or spirals?
Yes.
Yes, yeah.
They're very much so. There's definitely evidence that galaxies with bars have enhanced nuclear star formation. And there's a lot of ongoing debate in the observational community about whether there's a correlation between bars and AGN.
Just spirals, no bars?
I mean, that's a hard question to answer because the disk galaxies that don't have spirals are just super different to the ones that do have spirals. Maybe that's also the case for bars. Now I'm saying it out loud, but I mean, there definitely, you can find a sample of disk galaxies with spirals and no bar. You can definitely do that. But your sample of disk galaxies that doesn't have spirals, they're kind of weird, right? So they're more like lenticulars and things like that. And then there's a big mass difference as well. So I think it would be hard to answer that question. And it's the mass difference that's causing the debate, I think, with AGN and bars, where bars are more likely to more massive galaxies, AGN are more likely to more massive galaxies. So if you just do a simple correlation, yes, there are more AGNs in galaxies that have more bars. But if you do it more carefully, controlling for mass, it's less clear. But maybe a little bit of a link, yeah.
So you just mentioned passing lenticulars or S0s. What are your thoughts of how they fit in? People have been arguing this since Hubble, I think, about how they fit into this. Do you want to speculate, or what is the current consensus, if there is one?
Yeah, there's a really, really nice paper by Amelia Fraser-McKelvey on this. She was a postdoc who worked within MANGA, and that maybe yeah, big fan of morphology, and I do think you can get physics out of morphology, and there are morphologies where you can get unique sets of galaxies. Lenticulars might not be that, right? You might end up actually with more than one way to make a lenticular. And so Amelia's work actually was looking at differences between lenticulars. And there are some lenticulars that may well be faded spirals, so just spirals that, I mean, the slides I skipped were about red spirals. Red spirals are interesting and not that rare, and shouldn't last for a long time. So these are spirals that have no current active star formation. They should fade over time, and then maybe they form a lenticular. So this is one route, right? But certainly not all lenticulars can be this. So There's also the interesting thing that a lot of elliptical galaxies show significant rotation. So yeah, it's the disks all the way down.
The fact that we see so many of these things, if they're supposedly so short-lived.
I don't think there's any tension. I think it's just a common evolutionary route. Yeah, I don't think so. It's a good question.
Any final questions?
Question about Galaxy Zoo. Who is in charge of coming up with questions? And follow-up to that is, if someone were to have kind of an idea for a type of question that is more specific, is there a process for sort of proposing it?
Oh, that's a great question. We are very collaborative. So we have bi-weekly telecons, and when we have new sets of images, we discuss what the good classification set would be. Increasingly, our new sets of images are coming via some kind of agreement with the team that make the images, and so that team have specific things they want to have in the classification tree. We have a number of like side projects going, so like quick morphology questions, particularly like either or. There's a mobile app that is really good at like really quick either or questions. So if, for example, you were just searching for shells in the outskirts of galaxies, you could be like, do you see shells here? Yes, no. And that can be done really quickly in the mobile app. We've always been a fairly informal collaboration. So as I said, if you're interested in collaborating, reach out and we'd like to talk.
So find the arms and the R number by asking observers, asking your scientists to trace the arms and then taking some sort of mean. How well does that agree with what you would just get from Fourier analysis? Because which is of course closer to the dynamical theory. So
for sure.
For example, you say most are really n equals 2. What does that mean in terms of the power?
I've been meaning to. I have not measured that, and I don't think I've seen that comparison done so directly. But I've been meaning to do that because it's not that hard to do the Fourier analysis at some level, right? So, yeah, and I always wonder because this whole thing about the Milky Way, does it have 2 arms or 4 arms? And that very much depends on the band you look at, the kind of traces. Yeah, it's a good question, and it's something we should check. The arm number is not from tracing; it's just from asking people what they see. So, do you how many arms do you see in this galaxy? Yeah. What's interesting is that there isn't necessarily a single answer to that either. I said there's not necessarily a single pitch angle, but the number of arms can change with radius. So you can have really clear 2 arms in the center, and then it's just a big mess in the outskirts. So what you answer in that case, I don't know, but yeah.
Yeah, so you mentioned there are also some robotic ways to measure these things. Could you say more about that? And also, I mean, now recently there are development of the machine learning techniques, and I wonder how do you think that will be useful for these spiral study?
Yeah, so this is what we have going right now in Galaxy Zoo. So the crowdsourcing creates a training set, which is fed to ZooBot, is the name of our robot, which is very good at classifying the normal stuff where we have a good training set. And then it's in the loop. So stuff that doesn't have a high probability of a good classification gets fed back to the site. So this is working right now. This is Mike Walmsley's work, also Chris Lintott. Mike was an Oxford PhD student. He worked at Manchester for a while. He's now in Toronto. So come over to this side of the Atlantic, which is cool. Yeah, so I refer you to Mike's work on the machine learning in the loop at Galaxy Zoo. Mike's also been working some on image segmentation. So using our masks from Galaxy Zoo 3D to try to train image segmentation. This stuff is getting better, but generally we'll always need some kind of training set. So that's the sort of niche we've been discussing in Galaxy Zoo, of working with it in an integrated way to get the training set. A lot of the Galaxy Zoo classification, not citations to Galaxy Zoo, a lot of those are actually people using it to train a machine learner. So.
Current state of these machine learning, neural network-based machine learning is that still not as good as human being.
I mean, it starts to get hard to quantify, right? That they can agree with humans to sort of 90%, but if you set a population of humans to classify galaxies, they will also agree with each other to 80, 90%. It's a really cool paper from the 90s where someone did that with a bunch of galaxy classifiers.
What about the more traditional, statistical way to do the image processing? Like, is there any new algorithms now to measure, like, without the human guidance, just to do some analysis of
images? Yeah.
Measure the pitch angle, or identify spiral arms or something like that. Is there any progress on that? We have to rely on human beings still, like, to identify spiral, for example.
Yeah, I mean, it would be lovely, right, to be able to just feed the images to a computer and out you get really reliable pitch angles. I suspect it's going to be tricky for a long time. And I think, I do end up reading a bunch of machine learning papers. Actually was reading one not to do even with galaxies the other day for reasons to do with being a professor at a small liberal arts college, I guess. And even that computer science professor, like, buried in the paper was a bit where they had people look at the sets that they classified, which I was sort of like, oh, okay, so there's still people looking at stuff in this computer science paper to figure out what's coming out of the machine learner. And I think that's one of the sort of hidden secrets of all of these algorithms, is the amount of human effort that went into training them. So I don't know, I'm a bit of a skeptic, partly because spirals are so patchy and weird looking. And we were talking earlier, right? What even is the pitch angle, especially if you have these things where the gradient of the color and therefore maybe where the brightest light is, maybe switches side from the inner part to the outer part of the spiral. How does that impact the pitch angle? The pitch angles are not the same for every spiral in a galaxy, or not the same with function of radius. Is there even a single number for a pitch angle for a galaxy? So I think they are somewhat complicated objects that, I mean, it's like lots of places in astronomy, probably all sciences, right? Once you have a really detailed look at an object, it's much more complicated than you thought.
Okay. 1 minute, any last question? Matt?
I'm curious about the human element here, because humans are good at pattern recognition, but certain patterns more than others. So, I mean, if you just showed them, if you took a galaxy and plot it in log R and angle space, do people see more than if you just put it in X, Y?
Yeah, and there's the thing you can do to, like, unsharp masking and pull out features, right? We've not tried, like, weird projections. There's, I mean,
So you're just giving them the raw image.
Well, we give them a process image. We usually give them a 3-color image with a nice scaling so that features.
I mean, there's a sort of art to picking the right 3-color scaling and the image depth that makes a nice image. I mean, as you mentioned, it's people, so we have to get them to actually engage with the site. So there is a little bit of, like, the images. It helps if the images are somewhat attractive, although, which is easy with spiral galaxies. But there are the Galaxy Zoo works so well, it inspired this whole Zooniverse of citizen science projects. And some of the projects in that the data is less attractive. But if you motivate the question appropriately and say, we want to find exoplanets or something, people still are engaging with it. So maybe we could try different projections of galaxies if we think it's really necessary. But computers are pretty good at picking out straight lines, right? So if you think you've got log spirals in the right projection, you have straight lines. I don't know.
All right, there are a couple of spots left for dinner if anyone wants to sign up. Otherwise, let's go to the lunch and thank you, Harry.